3.5 billion years ago, our planet was unrecognizable. The oceans stretched endlessly beneath an alien sky, and in those primordial waters, something extraordinary was about to happen. Life was about to discover one of chemistry's most beautiful secrets. Before we continue this journey, tell us where you're tuning in from, and if this story resonates with you, make sure you're subscribed, because tomorrow I've saved something extraordinary for you. Picture, if you will, a world without light. No sun piercing the darkness of deep waters, no fire warming ancient shores, no stars visible through the thick atmosphere. Yet in this seemingly barren realm, the first bacteria were conducting an experiment that would change the nature of existence itself. They were learning to glow. These microscopic pioneers stumbled upon something that human technology wouldn't achieve for billions of years to come. They discovered how to transform simple molecules into pure light without producing heat. The reaction they mastered occurs in milliseconds. Luciferin molecules meeting oxygen in the presence of luciferase enzymes, releasing photons that pierced the primordial darkness like tiny beacons of hope. Consider the elegance of this process. Inside these ancient cells, a chemical dance was beginning that would eventually illuminate forests, paint the deep ocean with living stars, and inspire wonder in every human who witnessed it. The bacteria had achieved what we now recognize as nature's most efficient light source biological systems that convert 96% of their energy into illumination. To put this in perspective, our best LED bulbs manage only 20% efficiency. These ancient organisms were already perfect. But the true marvel isn't just the efficiency, it's the fact that life chose to create light at all. In a universe where darkness was the norm, where energy was precious and survival uncertain, these early cells invested in beauty. They made a decision that would echo through evolutionary time, that light was worth the cost. The secret spread slowly through the tree of life, passing from one generation to the next like a precious gift. Some bacteria learned to flash warnings when disturbed. Others used their glow to attract prey or communicate with their neighbors. Each species discovered its own way to wield this ancient power, but the fundamental chemistry remained unchanged, a testament to the perfection of that first discovery. Millions of years passed. The Earth's atmosphere changed, continents drifted, and complex life began to emerge from those primordial seas. But the bacteria's gift traveled with them. As creatures evolved gills and fins, shells and tentacles, many carried within their cells the same luminous chemistry that had first sparked in the depths of time. Fast forward now to 350 years before the Common Era. A Greek philosopher named Aristotle stood on Mediterranean shores, watching something that would puzzle him for the rest of his life. As waves crashed against the rocks, they burst into liquid starlight. The water itself seemed to burn with cold fire. Aristotle called it cold light, and he spent years trying to understand how the sea could illuminate without flame. He observed that certain fish glowed so brightly they could light up a fisherman's net. He noted that the luminescence appeared strongest when the water was disturbed, as if the ocean were responding to touch with cascades of light. What Aristotle was witnessing, though he couldn't know it, was the same chemistry that had begun 3 billion years earlier. The descendants of those first glowing bacteria still inhabited the seas, and when disturbed by waves or passing fish, they would flash their ancient warnings, turning the Mediterranean into a galaxy of living stars. Half a world away, Chinese scholars were documenting their own encounters with nature's light show. In the deep forests of ancient China, they found mushrooms that glowed like lanterns, illuminating mountain paths with an ethereal green radiance. They called these fungi ghost mushrooms, and believed they marked places where spirits dwelled. Local travelers would collect them in bamboo containers, creating the world's first biological flashlights for nighttime journeys. The Romans, too, had their encounters with living light. Pliny the Elder, the great naturalist of his time, wrote detailed accounts of fish that shone so brilliantly they could illuminate an entire room. He described them as carrying their own internal lamps, and wondered whether they might be divine creatures sent to guide sailors through treacherous waters. These ancient observers, scattered across continents and centuries, were all witnessing the same phenomenon, the enduring legacy of that first bacterial discovery. They couldn't know that the light they marveled at was produced by the same chemical reaction occurring in creatures as different as deep-sea fish and forest fungi. They couldn't understand that every flash they witnessed was powered by the same molecular machinery that had first ignited in primordial seas. But perhaps they sensed something deeper. Perhaps they recognized that this wasn't merely light, it was life itself choosing to shine. In their writings, there's a sense of reverence, a recognition that they were witnessing something sacred. They understood, in ways that sometimes escape our modern minds, that light emanating from living creatures represented a bridge between the physical and the mystical. The chemistry they observed was both simple and profound. Luciferin, the light-bearing molecule, had evolved into countless variations across different species, yet its essential function remained constant. When this substrate met its enzyme partner, luciferase, in the presence of oxygen, the reaction released photons with a precision that would make a physicist weep. No energy wasted as heat, no inefficient burning, just pure, cold light emerging from the careful orchestration of molecules. This process, which we now call bioluminescence, represents one of evolution's most elegant solutions to the challenge of communication in darkness. Over billions of years, life had experimented with countless ways to signal, warn, attract, and deceive, but few innovations proved as versatile or enduring as the ability to generate light from within. Think about the profound implications of this discovery. In a universe where energy follows strict laws of conservation, where every joule expended must serve survival, these ancient bacteria chose to spend their precious resources on creating beauty. They invested in light, not because they needed to see many lived in environments where vision was impossible, but because they had found ways to make light serve life. Some used their glow as a burglar alarm, flashing warnings when predators disturbed them. Others employed it as a lure, drawing prey close with hypnotic displays. Still others discovered that light could serve as a language, allowing them to communicate complex messages across the darkness. Each strategy was a variation on the same theme. Light as a tool for survival, light as a bridge between organisms, light as a way of writing messages in the darkness. As we trace this story from its ancient origins, we begin to see that bioluminescence is more than just a biological curiosity. It's a fundamental expression of life's creativity, proof that even the smallest organisms can harness forces that seem almost magical. The bacteria that first learned to glow were pioneer engineers, developing technologies that we're only now beginning to fully appreciate and replicate. Their discovery would eventually illuminate the deepest ocean trenches, guide fireflies to their mates on summer evenings, and provide scientists with tools to peer inside living cells. It would inspire countless myths and legends, fuel human imagination, and remind us that the boundary between science and wonder is often thinner than we imagine. But perhaps most importantly, that first spark of biological light in Earth's ancient oceans established a principle that continues to guide life today, that beauty and function need not be separate, that efficiency and elegance can coexist, and that even in the darkest places, life finds ways to shine. The story of bioluminescence is ultimately the story of life's endless creativity. It reminds us that we inhabit a world where the impossible happens every day, where organisms routinely perform feats that challenge our understanding of what's possible. From those first glowing bacteria to the countless species that carry their luminous legacy today, we see evidence of nature's inexhaustible capacity for innovation. As we prepare to dive deeper into this luminous world, to explore the creatures that have mastered light in ways that continue to amaze us, Remember that every flash we'll encounter traces back to that moment 3.5 billion years ago, when life first learned to glow. In studying bioluminescence, we're not just learning about chemistry or biology, we're witnessing the continuation of one of life's oldest and most beautiful experiments. Tomorrow, we'll descend into the depths where William Beebe first glimpsed the true extent of nature's light show, where entire ecosystems pulse and glow in the eternal darkness of the deep sea. We'll discover a world where light has become the primary language of life, where creatures paint with photons in ways that would make human artists envious. But tonight, as you drift towards sleep, carry with you this thought. Somewhere in the darkness around you, in puddles and ponds, in soil and sea, the descendants of those first glowing bacteria continue their ancient work. They flash their quiet signals, tend their molecular fires, and remind us that light, true light, comes not from burning, but from living. The year was 1934, and humanity was about to glimpse a world that would forever change our understanding of life on Earth. In the waters off Bermuda, a steel sphere no larger than a telephone booth bobbed on the Atlantic surface, preparing for a journey into the unknown. William Beebe, naturalist and explorer, squeezed himself into this cramped vessel called the bathysphere. Through a single porthole barely 8 inches across, he would become the first human being to witness what lay hidden in the ocean's middle depths. As the winch began to lower his metal cocoon, Beebe had no idea he was about to discover an entire universe of living light. At 100 feet below the surface, the familiar blue of shallow water began to deepen. Sunlight, that constant companion of terrestrial life, started its inexorable fade, but Beebe was descending toward something far more spectacular than mere darkness. He was approaching the realm where life had learned to replace the sun with something infinitely more magical. At 300 feet, the first stars appeared. "My God," Beebe radioed to the surface, his voice crackling with static and wonder. A jellyfish had drifted past his porthole, not the translucent, passive creature he might have expected, but a living constellation. Its bell pulsed with rings of blue light, each contraction sending waves of luminescence rippling through its transparent body like electricity through glass. But this was only the beginning. As the bathysphere continued its descent, passing through 500, then 800 feet, Beebe's world transformed into something that seemed to belong more to science fiction than scientific observation. Fish swam past, carrying their own headlights, their photophores arranged in patterns as unique as fingerprints. Some wore strings of lights along their sides like living Christmas trees. Others carried lanterns that swayed hypnotically in the current. At 1,000, a feet below the surface, Beebe made a discovery that would revolutionize our understanding of deep-sea life. He wasn't observing a few scattered creatures that happened to glow. He was witnessing an entire ecosystem built around light. Fish communicated in flashing codes. Squid ejected clouds of luminous ink that sparkled like underwater fireworks. Jellies created rippling light shows that stretched as far as his limited vision could reach. The statistics, when scientists later compiled them, were staggering. Beebe had discovered that 96% of deep-sea creatures create their own light. In the ocean's depths, bioluminescence wasn't an exotic rarity, it was the norm. Life had taken the sun's abandonment and turned it into an opportunity for innovation beyond human imagination. Consider what this means. In the vast volume of water that makes up our planet's deep ocean, a realm that represents 99% of Earth's living space, darkness has become a canvas for one of nature's most spectacular art forms. Every flash Beebe witnessed represented millions of years of evolutionary refinement, each pattern a solution to the fundamental challenges of life in perpetual night. The creatures Beebe encountered had developed light-based technologies that put human engineering to shame. Deep-sea fish had evolved adjustable spotlights that could be dimmed or brightened at will. Their photophores contained sophisticated lens systems that could focus light into narrow beams or spread it into wide floods. Some species had even developed the biological equivalent of colored filters, producing red light invisible to most predators but perfectly visible to members of their own species. 20 years after Beebe's pioneering descent, Auguste Piccard pushed even deeper into this luminous realm. His bathyscaphe Trieste was built to withstand pressures that would crush the bathysphere like an eggshell. In 1960, Piccard and Don Walsh descended to the deepest point on Earth, the Challenger, deep in the Mariana Trench, 7 miles beneath the Pacific's surface. Here, in a place where the pressure exceeds 1,000 times that at sea level, where the weight of water above could flatten a car in an instant, they expected to find a barren wasteland. Instead, they discovered that life's light show extended even to these ultimate depths. Through their porthole, they watched creatures that seemed to belong to another planet entirely. The journey to these depths reveals the true scale of bioluminescence's domain. Imagine descending through layer after layer of living light, each zone populated by creatures that have mastered illumination in their own unique ways. In the twilight zone, between 600 and 3,000 feet deep, vampire squid unfurl their arms to create bioluminescent galaxies. Their bodies can produce light in any pattern imaginable: dots, dashes, spirals, or solid glows that make them appear to be made of liquid starlight. Further down, in the midnight zone where no trace of sunlight ever penetrates, giant tube worms host colonies of glowing bacteria. These bacterial partners paint the ocean floor in living constellations, creating scenes that look more like alien cities than earthly seafloor. The worms themselves can grow longer than a human is tall, yet they depend entirely on their microscopic light-producing tenants for survival. But perhaps the most remarkable discovery was how these creatures use light as a language. Deep-sea fish flash complex patterns that serve as identification codes, allowing them to recognize members of their own species in the vast darkness. Squid create traveling waves of light across their skin, communicating emotions and intentions through patterns that shift and flow like liquid neon signs. Some creatures had evolved light-based hunting strategies that seem almost impossibly sophisticated. The anglerfish, hanging motionless in the water column, waves a glowing lure that mimics the movements of prey. Small fish, drawn by this hypnotic light, swim directly into the predator's enormous jaws. The anglerfish's lure contains millions of specialized bacteria that produce light 24 hours a day, creating a biological fishing rod that never needs batteries. Other species use bioluminescence for defense in ways that border on the magical. When threatened, certain deep-sea jellies detach their glowing body parts, creating a cloud of pulsing decoys while they escape into the darkness. It's the biological equivalent of a fighter pilot releasing flares to confuse incoming missiles, but infinitely more elegant. The burglar alarm strategy, evolved by many deep-sea creatures, represents one of nature's most clever uses of light. When a small organism is attacked by a predator, it releases a burst of bioluminescence that acts like a beacon, attracting larger predators to the scene. The attacker, suddenly illuminated and vulnerable, often retreats rather than risk becoming prey itself. It's a system of biological security lighting that would impress any modern engineer. As exploration technology improved, scientists discovered that the light shows observed by Beebe and Piccard were just the beginning. Advanced submersibles equipped with sensitive cameras revealed that bioluminescence creates patterns visible from space. Satellite images show vast blooms of bioluminescent plankton, turning entire sections of ocean into glowing seas that can be seen from orbit. These planktonic displays represent some of the largest coordinated light shows on Earth. When disturbed by waves, schools of fish, or even submarines, billions of single-celled organisms flash in unison, creating waves of light that roll across the ocean's surface like biological aurora. Each individual flash lasts only 1/10 of a second, but when millions of organisms respond together, they create illumination bright enough to read by. The discovery of deep-sea bioluminescence fundamentally changed our understanding of life's possibilities. Before BB's descent, scientists believed that complex ecosystems required sunlight. The deep ocean was thought to be a biological desert, sparsely populated by creatures eking out a meager existence on the scraps that drifted down from above. Instead, explorers found a realm where life had not merely survived the absence of sun, it had thrived. The deep ocean revealed itself to be perhaps the most creative laboratory on Earth, a place where evolution had millions of years to experiment with light-based technologies in isolation from surface influences. Each dive into these depths continues to reveal new species wielding light in ways that challenge our imagination. Fish that create holographic displays with their bioluminescence, jellies that coordinate their flashing across miles of ocean, bacteria that can adjust their light output based on population density, creating biological dimmer switches that respond to crowding. The tools used by modern deep-sea explorers would seem magical to Beebe. High-definition cameras capture the precise wavelengths and intensities of bioluminescent displays. Spectrometers analyze the exact chemistry behind each flash. Remotely operated vehicles allow scientists to observe these creatures in their natural habitat without the disturbance caused by human presence. One of the most significant breakthroughs came when marine biologist Edith Widder realized that traditional submarine lights were actually scaring away the very creatures scientists wanted to study. The bright white lights used by early submersibles were like shining stadium floodlights into a world adapted for subtle communication through gentle glows. Widder developed stealth camera systems that used red light, invisible to most deep-sea creatures, allowing researchers to observe natural behaviors for the first time. Her electronic jellyfish lures, which mimicked the bioluminescent, distress signals of real jellies, revolutionized deep-sea observation. These artificial displays attracted creatures that had remained hidden from human eyes for centuries, including giant squids that had achieved almost mythical status among marine biologists. The footage captured by these new technologies revealed that the deep ocean is in constant conversation. Light flashes carry information across vast distances, coordinating behaviors that span entire ocean basins. Migration patterns, feeding strategies, and reproductive cycles are all orchestrated through bioluminescent signals that create a global communication network beneath the waves. Today's deep-sea research vessels are equipped with instruments that can detect individual photons, allowing scientists to study even the faintest bioluminescent signals. They've discovered that some deep-sea creatures produce light so dim it would be invisible to human eyes, yet perfectly visible to other members of their species. These subtle displays represent a kind of whispered conversation in the darkness, intimate communications that escape casual observation. The journey from Beebe's cramped bathysphere to today's sophisticated deep-sea observatories represents more than just technological progress. It reflects our growing appreciation for the creativity and complexity of life in Earth's most challenging environments. Each new discovery in the deep ocean reminds us that we share our planet with beings whose abilities routinely exceed the boundaries of human imagination. As we prepare to explore how scientists finally cracked the code of bioluminescence, remember that every formula and mechanism we'll discover was first glimpsed through the portholes of brave explorers descending into living galaxies. The chemistry that powers these displays had been perfected over hundreds of millions of years before humans ever dreamed of diving beneath the surface. The deep ocean's light show continues every night, whether we're there to witness it or not. In trenches and abyssal plains, on underwater mountains and in the vast spaces between, creatures paint with photons in displays that would humble any human artist. They remind us that some of nature's most spectacular performances take place far from human eyes, in theatres so remote that we've only just begun to discover them. Tomorrow, we'll journey into laboratories, where scientists ground up glowing creatures to unlock the secrets of cold light, forever changing our understanding of the chemistry that makes these underwater galaxies possible. In a dimly lit laboratory in Lyon, France, The year 1885 marked the beginning of humanity's greatest detective story. French physiologist Raphael Dubois stood before his workbench, surrounded by jars containing creatures that defied explanation. Glowing clams pulsed with ethereal light. Fireflies blinked their last signals in glass containers. And Dubois was about to perform an experiment that would finally reveal the secret that had puzzled humanity since Aristotle first watched the Mediterranean burn with cold fire. For thousands of years, bioluminescence had remained nature's most beautiful mystery. Philosophers and naturalists had observed it, poets had celebrated it, but no one understood how living creatures could produce light without flame, without heat, without any of the mechanisms that humans associated with illumination. Dubois was about to change all that. The breakthrough came through an act of scientific destruction that led to creation. Dubois carefully ground up his precious specimens, grinding clams and fireflies until their magical glow disappeared entirely. To most observers, this would have seemed like vandalism, the destruction of beauty in service of cold science. But Dubois understood that sometimes we must break things apart to understand how they work. From the lifeless pulp, he began the delicate process of separation. Using techniques that were revolutionary for his time, Dubois isolated the light-making machinery into its component parts. What he discovered would forever change our understanding of life's most elegant chemistry. He found two essential components, both necessary but neither sufficient alone. The first he named luciferin, after Lucifer, the light-bearer of ancient mythology. This molecule, he discovered, stored energy like a miniature battery, waiting for the right conditions to release its luminous potential. The second component he called luciferase, an enzyme that acted as the key to unlock luciferin's stored light. The moment of revelation came when Dubois mixed these separated components together in the presence of oxygen. The dead, ground-up remains of his specimens suddenly blazed with the same cold light that had once emanated from living creatures. He had achieved something that bordered on resurrection, bringing light back from the chemical grave. But this was more than just scientific triumph. Dubois had uncovered nature's most elegant solution to an impossible problem. Consider the challenge that life faced: how to create light without the devastating heat that accompanies combustion. Human attempts at artificial lighting invariably produced enormous amounts of waste heat. Candles burned, oil lamps burned, even the electric bulbs that were just beginning to illuminate cities in Dubois's time converted most of their energy to heat rather than light. Yet here, in the delicate chemistry of living creatures, was a system that achieved what human technology could barely imagine: a cold light production, with an efficiency that approached perfection. The reaction that Dubois had recreated in his laboratory converted 96% of its energy directly into photons, with virtually no waste heat. To put this in perspective, our most advanced LED bulbs today achieve only about 20% efficiency. The chemistry that Dubois discovered operates on principles that seem almost magical in their precision. Inside every glowing creature, luciferin molecules exist in a state of patient readiness. When luciferase enzymes encounter these molecules in the presence of oxygen, they facilitate a reaction that occurs in less than 1/1000th of a second. During this brief moment, electrons within the luciferin molecule absorb energy and jump to higher orbital levels. As these excited electrons fall back to their ground state, they release their excess energy as photons, particles of pure light that escape the molecule and illuminate the surrounding world. The elegance of this process becomes even more remarkable when we consider its universality. From the bacteria that first discovered bioluminescence 3 billion years ago, to the fireflies blinking in Dubois' laboratory, the fundamental chemistry remained essentially unchanged. Evolution had stumbled upon a solution so perfect that it required no improvement across vast spans of geological time. Yet within this universal framework, life had created an astounding diversity of variations. Different species had evolved their own unique versions of luciferin, each adapted to specific environmental needs and biological functions. Some luciferins produced blue light that traveled farthest through seawater. Others created green illumination optimal for communication through forest canopies. Still, others generated red light invisible to most predators but perfectly visible to potential mates. The breakthrough discoveries didn't end with Dubois. In 1962, Japanese scientist Osamu Shimomura was walking along the shores of Friday Harbor in Washington state when he noticed something extraordinary. Crystal jellies, those ethereal creatures that drift through northern Pacific waters, were washing up on the beach in unusual numbers. Most researchers would have seen an opportunity to study these beautiful animals in their natural state. Shimomura saw something different, a chance to understand how some creatures create green light from blue. Shimomura's subsequent research revealed one of nature's most sophisticated optical systems. He discovered that crystal jellies don't simply produce green light directly. Instead, they use a two-step process that rivals the complexity of human-engineered lighting systems. The primary bioluminescent reaction creates blue light through the traditional luciferin luciferase pathway. But then, a secondary protein called green fluorescent protein absorbs this blue light and re-emits it as green nature's own color conversion system. This discovery revolutionized more than just our understanding of bioluminescence. The green fluorescent protein that Shimomura isolated became one of the most important tools in modern medical research. Scientists learned to attach this protein to cancer cells, allowing them to track tumor growth in real time. They could watch as experimental treatments reached their targets, observe as cells divided and died, and monitor the progression of diseases through living tissue with unprecedented clarity. The implications of these discoveries rippled through scientific understanding like light through water. Researchers realized that bioluminescence wasn't just a curiosity, it was a window into fundamental principles of chemistry and physics. The efficiency of biological light production challenged engineers to rethink their approaches to artificial illumination. The precision of biochemical reactions inspired new techniques for controlling molecular processes. But perhaps most importantly, the chemistry of bioluminescence revealed the extraordinary sophistication hidden within seemingly simple living systems. Each flash of a firefly represented the coordinated action of millions of molecules, all working together with clockwork precision to create a single photon of light. Each pulse of a deep-sea creature involved cellular machinery more complex than any human-built factory. The tools that modern researchers use to study bioluminescence would seem magical to Dubois and Shimomura. High-speed cameras can capture individual flashes lasting mere milliseconds, revealing the precise timing and intensity of bioluminescent displays. Spectrometers analyze the exact wavelengths of biological light, identifying the specific chemical pathways involved in its production. Genetic sequencing allows scientists to trace the evolutionary history of bioluminescence, understanding how different species acquired and modified their light-producing abilities. These advanced techniques have revealed that the basic luciferin-luciferase reaction discovered by Dubois has been modified and refined by evolution in countless ways. Some creatures use additional cofactors helper molecules like ATP, magnesium ions, or specialized proteins to enhance or control their light production. Others have developed cellular structures called photophores that focus and direct their bioluminescent output like biological spotlights. The diversity of bioluminescent chemistry reflects the variety of functions that light serves in the natural world. Fireflies use specialized cells in their abdomens that can be switched on and off with neurological precision, allowing them to create complex flashing patterns for mate recognition. Deep-sea fish employ bacteria that live symbiotically in specialized organs, creating biological partnerships that benefit both species. Fungi produce continuous glows through chemical reactions that proceed slowly and steadily, creating reliable beacon lights in forest environments. Each of these systems represents a different solution to the fundamental challenge of biological light production: how to create photons efficiently while maintaining precise control over when, where, and how much light is produced. The answers that evolution has developed span the full spectrum of possibility, from simple bacterial reactions to complex multi-protein systems that rival human engineering in their sophistication. Modern research has also revealed the crucial role that cellular organization plays in bioluminescence. The reaction itself may be simple, but controlling it requires elaborate cellular machinery. Specialized organelles store and protect light-producing chemicals. Membrane systems regulate the flow of oxygen and other reactants. Neural networks coordinate the timing of flashes across an organism's entire body. The study of bioluminescent chemistry has led to breakthrough applications that extend far beyond scientific curiosity. Medical researchers use modified luciferase to track the effectiveness of new drugs, watching as treatments spread through the body and reach their intended targets. Environmental scientists employ bioluminescent bacteria as living sensors, using their light output to detect pollution levels in water supplies. Space agencies investigate bioluminescence as a potential source of sustainable lighting for long-duration missions where traditional power sources would be impractical. But perhaps the most profound impact of understanding bioluminescent chemistry has been its effect on our perception of life itself. The precision and efficiency of biological light production reminds us that living systems routinely accomplish feats that challenge our most advanced technology. Every creature that glows carries within its cells machinery more sophisticated than our finest instruments, operating with an efficiency that makes our best efforts seem crude by comparison. The chemistry that Dubois first unlocked in his laboratory continues to inspire wonder and innovation more than a century later. Each new discovery reveals additional layers of complexity and elegance in systems that initially appear simple. The more we learn about bioluminescence, the more we appreciate the extraordinary creativity and problem-solving capability of evolution itself. As we prepare to explore the spectacular displays created by these chemical reactions, from firefly meadows to bioluminescent bays, remember that every flash we'll witness represents the culmination of billions of years of chemical refinement. The luciferin and luciferase that power these displays have been tested and perfected across geological time, creating light shows that combine scientific precision with artistic beauty. The code of living light, once cracked by curious scientists grinding up glowing creatures, continues to reveal new secrets. Each laboratory experiment, each field observation, each technological application adds another piece to our understanding of how life learned to paint with photons. The story that began with Dubois's simple separation of light-making chemicals has become an epic tale of molecular engineering that spans from the primordial past to the technological future. Tomorrow, we'll witness the results of all this chemical artistry as we explore nature's most spectacular light shows, where the precise reactions discovered in laboratory conditions create displays that inspire wonder in every human fortunate enough to witness them. Every summer evening in the Great Smoky Mountains, as twilight deepens and the first stars appear, something magical begins to stir in the forest. Among the ancient trees that have stood for centuries, thousands of tiny lights begin to flicker. But these are not electric bulbs or candles. They are living creatures preparing for one of nature's most romantic performances. The synchronous fireflies of Photinus carolinus gather for just 2 weeks each June, transforming entire hillsides into pulsing galaxies of golden light. What makes this display extraordinary is not simply the number of participants, though thousands of males do join the chorus, but the precision of their coordination. These insects flash in perfect unison, their timing so exact that the entire forest appears to breathe with light. Imagine witnessing this phenomenon for the first time. As darkness settles over the mountains, individual fireflies begin their evening warm-up, flashing sporadically like scattered sparks. Then, gradually, something remarkable happens. The random flashes begin to align. One firefly adjusts its timing to match its neighbor. Another joins the growing chorus. Within minutes, what began as chaos transforms into a symphony of light that pulses across the mountainside with the rhythm of a giant heartbeat. Scientists still debate exactly how these insects achieve such precise coordination across entire hillsides. Each male carries within his abdomen a sophisticated biological timing system more accurate than many human-made clocks. Specialized cells called photocytes can be switched on and off with neural precision, allowing fireflies to control not just when they flash, but how long each pulse lasts and how bright it appears. The male fireflies are not simply showing off, they are participating in a courtship ritual that has been refined over millions of years. Each flash is a carefully crafted advertisement, a luminous resume that communicates the flash's species, health, and genetic quality. The females, watching from the forest floor and lower vegetation, judge these displays with discrimination that would impress any critic. What the females are evaluating goes far beyond simple brightness. They assess the consistency of flash patterns, the duration of each pulse, and the male's ability to maintain synchronization with his neighbors. A firefly that can flash brightly and regularly, while maintaining perfect timing with thousands of other males, demonstrates genetic quality and physical fitness that make him an attractive mate. But the males face a challenging balancing act. Each flash represents a significant energy expenditure. The chemical reactions that produce their light and consume precious resources that could otherwise be used for survival and reproduction. A firefly that doubles his flash. Brightness burns 4 times more energy, but can attract females from twice the distance. Evolution has fine-tuned this trade-off, creating optimal solutions that maximize reproductive success while minimizing energy waste. The chemistry powering these displays operates with efficiency that makes human lighting technology seem primitive. Inside each firefly's lantern, luciferin molecules combine with luciferase enzymes in the presence of oxygen and ATP to create cold light with 96% efficiency. Compare this to incandescent bulbs, which convert only 4% of their energy to visible light, wasting the rest as heat. The firefly's system produces virtually no waste heat, allowing these insects to flash repeatedly without overheating their delicate bodies. Move now from the mountain forests to tropical seas, where an entirely different kind of light show unfolds each night. In warm coastal waters around the world, microscopic organisms called dinoflagellates create displays that transform the ocean into liquid starlight. These single-celled creatures, each smaller than the period at the end of this sentence, possess the power to turn breaking waves into cascades of blue fire. Mosquito Bay in Puerto Rico hosts the most spectacular of these displays. Here, in waters that appear perfectly ordinary during daylight hours, approximately 700,000 dinoflagellates drift in every gallon of seawater. When darkness falls and the water is disturbed by a swimming fish, a breaking wave, or a human hand trailing through the surface, these tiny organisms respond with flashes that last just 1/10 of a second, but create illumination bright enough to read by. The dinoflagellates flash, not for reproduction or communication, but as a defense mechanism that represents one of nature's most clever security systems. When a predator disturbs the water while hunting, the resulting burst of bioluminescence serves as a biological burglar. Alarm. The sudden illumination startles the hunter while simultaneously attracting larger predators to the scene. Faced with the choice between continuing their attack or becoming prey themselves, most predators choose retreat. This strategy works because the bioluminescent flash creates a no-win situation for would-be predators. Small fish hunting dinoflagellates suddenly find themselves outlined in light, visible to larger fish that might see them as dinner. It's an elegant solution that turns the very act of predation into a liability, protecting entire populations of these microscopic light producers through collective defense. The biochemistry behind dinoflagellate bioluminescence operates on principles similar to firefly light production, but with important modifications that suit an aquatic lifestyle. Their luciferin, called luciferin, combines with luciferase and specialized organelles called scintillons. These cellular structures can discharge their contents in milliseconds, creating the rapid flashes that make disturbed water appear to sparkle with stars. Deep in ancient forests, far from both mountain meadows and tropical seas, another form of bioluminescence creates its own subtle magic. Honey mushrooms, those vast fungal networks that can spread across thousands of acres, occasionally reveal their presence through ethereal foxfire that pioneers called fairy light. These ghostly glows appear when conditions are just right, usually during warm, humid nights when the forest air hangs heavy with moisture. The honey mushroom networks represent some of the largest and oldest living organisms on Earth. Individual networks can live for over 2,000 years, their underground mycelium threads connecting trees across entire forests in a communication system that ecologists call the Wood Wide Web. Occasionally, when these fungal highways are disturbed or stressed, they emit a soft green glow that can illuminate forest floors with the gentleness of moonlight filtered through leaves. The purpose of fungal bioluminescence remains one of biology's enduring mysteries. Unlike fireflies seeking mates or dinoflagellates defending themselves, mushrooms appear to glow for reasons that scientists are still working to understand. Some researchers believe the light helps spores find suitable landing spots, guiding them toward areas where germination is most likely to succeed. Others suggest that the glow may be a side effect of metabolic processes, beautiful but incidental to the fungus's primary functions. What we do know is that fungal bioluminescence operates through a chemical pathway distinct from both fireflies and dinoflagellates. Mushrooms use a compound called fungal luciferin that reacts with a unique enzyme system to produce their characteristic green light. The reaction requires oxygen and proceeds slowly and steadily, creating the continuous glows that can persist for hours under favorable conditions. These three examples, mountain fireflies, ocean dinoflagellates, and forest fungi, represent just a tiny sample of the light shows that occur every night across our planet. In tropical rainforests, glowing bacteria paint fallen logs with patterns that shift and flow like liquid neon. In deep cave systems, larvae of fungus gnats create stellar displays on cave ceilings, their silk threads adorned with droplets of bioluminescent glue that attract prey like living constellations. Each of these displays represents a different solution to the fundamental challenges of life. Fireflies use light to find mates in the vast darkness of night. Dinoflagellates employ it as a sophisticated defense system that turns their small size into an advantage. Fungi may use their glow to guide reproductive spores, or simply as a byproduct of their complex metabolic processes. But beyond their individual functions, these bioluminescent displays serve a deeper purpose in Earth's ecological systems. They create beauty that enriches our world in ways that pure survival cannot explain. A firefly could presumably find mates through chemical signals alone. Dinoflagellates could defend themselves through toxins rather than light. Fungi could reproduce without any illumination whatsoever. Yet evolution has consistently favored solutions that combine function with beauty, efficiency with elegance. The result is a world where utility and wonder intertwine at the most fundamental levels of life. Every night, across every continent and in every ocean, creatures paint with photons in displays that would challenge the imagination of any human artist. The timing of these displays follows rhythms that connect individual organisms to cosmic cycles. Fireflies synchronize their flashing not just with each other, but with the phases of the moon, the seasons of the year, and the rotation of the Earth itself. Dinoflagellates bloom in response to ocean temperatures, nutrient levels, and tidal cycles that span months or years. Fungi time their glowing to coincide with periods of maximum spore release and optimal dispersal conditions. These rhythms remind us that bioluminescence is not random decoration, but integral architecture of Earth's living systems. The light shows we witness represent the visible expression of ecological processes that operate on scales from molecular to planetary. Each flash connects individual organisms to the larger web of life that encompasses our entire planet. Modern technology allows us to study these displays with precision that would amaze early naturalists. High-speed cameras capture the exact timing of firefly flashes, revealing subtle variations that encode information about species identity and individual fitness. Satellite imagery tracks dinoflagellate blooms across entire ocean basins, showing how these microscopic organisms influence global marine ecosystems. Chemical analysis reveals the precise molecular mechanisms that power fungal glows, connecting forest, light shows to fundamental processes of decomposition and nutrient cycling. Yet for all our technological sophistication, the direct experience of witnessing these natural light shows retains a power that scientific understanding cannot diminish. Standing in a meadow filled with synchronous fireflies connects us to wonder in ways that transcend intellectual appreciation. Swimming through bioluminescent plankton creates memories that bypass rational thought and speak directly to our sense of magic and possibility. Perhaps this is the deepest lesson these displays offer, that beauty and function need not be separate, that the natural world routinely creates spectacles that serve both survival and wonder. In studying bioluminescence, we discover that efficiency and elegance can coexist, that the most practical solutions often turn out to be the most beautiful. As we prepare to meet the modern scientists who dedicate their lives to understanding these phenomena, remember that every light show we've explored continues to unfold every night, whether we're present to witness it or not. In mountains and oceans, forests and caves, creatures continue their ancient practice of painting with light, creating beauty that enriches our world simply by existing. Tomorrow, we'll follow researchers into the field as they use cutting-edge technology to unlock the remaining secrets of bioluminescence, discovering new species and new applications that promise to transform our understanding of what's possible when life learns to glow. In the deep waters off California's coast, marine biologist Edith Widder floated in complete darkness, surrounded by the crushing weight of the Pacific Ocean. 3,000 feet above her head, the last traces of sunlight had long since faded to black. But Widder wasn't concerned with the sun's light. She was hunting for something far more elusive and magnificent. She was tracking the living stars of the deep sea. The year was 1993, and Widder was about to revolutionize deep-sea exploration with a realization that seems obvious in hindsight but was revolutionary at the time. For decades, marine biologists had descended into the ocean's depths with powerful floodlights blazing, illuminating their surroundings with the intensity of stadium lighting. They wondered why so many creatures seemed to flee their approach, why the deep sea appeared less populated than they expected. Widder understood what others had missed. In a world where creatures had evolved to communicate through subtle flashes and gentle glows, the bright white lights of traditional submersibles were like detonating fireworks in a library. Every time scientists tried to observe deep-sea life, they were announcing their presence with an intensity that terrified the very animals they hoped to study. Her solution was elegantly simple yet technologically sophisticated. Widder developed camera systems that used red light wavelengths that travel poorly through seawater and remain invisible to most deep-sea creatures. For the first time in the history of marine biology, humans could observe the deep ocean's inhabitants behaving naturally, unaware that they were being watched. The footage captured by these stealth systems revealed a world that had remained hidden from human eyes since the beginning of exploration. Deep-sea creatures that had never been filmed in their natural state suddenly appeared in unprecedented detail. Giant squids, those legendary behemoths that had inspired countless maritime myths, emerged from the darkness to investigate Widder's electronic lures. These lures represented another breakthrough in Widder's approach to deep-sea research. Rather than trying to attract creatures with bright lights or bait, she created electronic devices that mimicked the bioluminescent distress signals of real deep-sea animals. Her artificial jellyfish pulsed and flashed with patterns identical to those produced by creatures under attack, creating irresistible signals that drew predators from vast distances. The results exceeded even Widder's optimistic expectations. Her electronic lures attracted species that had eluded scientists for centuries. The footage they captured showed giant squids not as the aggressive monsters of maritime legend, but as curious, intelligent creatures investigating what appeared to be an easy meal. These encounters provided the first clear observations of how these magnificent animals actually behave in their natural environment. But Widder's innovations represented more than just technological advancement. They embodied a fundamental shift in how scientists approach the study of bioluminescence. Earlier researchers had focused on capturing and studying creatures in laboratory conditions, learning about their biochemistry by removing them from their natural context. Widder pioneered techniques that allowed scientists to study bioluminescence as it actually functions in nature, revealing behaviors and interactions that laboratory studies could never capture. Today's bioluminescence researchers have access to tools that would seem magical to the pioneers who first ground up fireflies and jellyfish to understand their chemistry. High-speed cameras can capture individual photons, recording flashes that last mere milliseconds with clarity that reveals every detail of their intensity and duration. These cameras operate at frame rates thousands of times faster than human vision, slowing down bioluminescent displays to reveal subtleties invisible to direct observation. Submersibles equipped with spectrometers can analyze the exact wavelengths of light produced by deep-sea creatures, identifying the specific chemical pathways responsible for each glow. This technology has revealed that different species often produce slightly different colors of light, creating a spectrum of hues that allows creatures to communicate on private wavelengths, invisible to potential predators or competitors. The precision of modern instruments has uncovered layers of complexity in bioluminescent displays that earlier scientists never suspected. Firefly flashes that appear uniform to human eyes actually contain subtle variations in intensity and color that encode detailed information about the flasher's identity, location, and reproductive status. Deep-sea creatures produce light shows with timing precise to millionths of a second, coordinating displays across vast distances through mechanisms that scientists are still working to understand. In the cloud forests of Costa Rica, researchers track creatures that produce some of the brightest biological light known to science. Click beetles of the genus Pyrophorus carry 3 separate light organs, 2 on their thorax that help them navigate during flight and 1 on their abdomen used for mate communication. These thumbnail-sized insects generate illumination over 10 times brighter than fireflies, creating light intense enough to read by when several beetles are placed together. The brightness of these beetle displays puzzled scientists until they discovered the insect's unique lifestyle. Unlike fireflies, which flash briefly and intermittently, click beetles maintain their glow for extended periods while flying through dense forest canopies. Their exceptionally bright bioluminescence allows them to navigate through complex 3-dimensional environments where dimmer lights would be insufficient for effective communication. Local people in Costa Rica discovered the practical applications of these living lanterns long before scientists understood their biology. Indigenous communities would collect click beetles in perforated gourds, creating biological flashlights that provided reliable illumination for nighttime activities. These living lamps required no fuel, produced no heat, and could be recharged simply by feeding the beetles and allowing them to rest during daylight hours. Modern researchers studying these beetles use techniques that combine traditional fieldwork with cutting-edge technology. Motion-activated cameras record their natural behaviors without human interference. Genetic analysis reveals how different populations have evolved variations in their bioluminescent chemistry. Chemical studies identify the specific luciferin compounds that enable such bright displays, providing insights that may lead to new applications in human technology. The study of marine bioluminescence has been revolutionized by advances in underwater robotics and sensor technology. Autonomous underwater vehicles can now patrol the deep ocean for months at a time, recording bioluminescent displays across vast areas without human presence. These robotic observers have revealed that many deep-sea creatures follow complex migration patterns, rising toward the surface at night and descending to greater depths during daylight hours. This vertical migration, known as the daily vertical migration, represents the largest movement of animals on Earth. Every night, billions of bioluminescent creatures rise from the depths, creating layers of living light that move through the water column like slow-motion fireworks. Acoustic sensors can track these migrations by detecting the sounds produced by swimming animals, while optical sensors record the light shows that accompany these massive movements. The data collected by these automated systems has revealed patterns in deep-sea bioluminescence that span entire ocean basins. Seasonal variations in light production correlate with reproduction cycles, food availability, and oceanographic conditions. Climate change appears to be affecting these patterns, with some species shifting their migration timing or depth ranges in response to changing water temperatures. Researchers studying freshwater bioluminescence have made equally remarkable discoveries using innovative techniques adapted to different environments. In lakes and the rivers around the world, scientists use underwater cameras equipped with motion sensors to record the light displays of aquatic organisms without disturbing their natural behaviors. These studies have revealed that freshwater bioluminescence is far more common than previously believed, with numerous species producing light shows that rival their marine cousins. The application of molecular biology techniques to bioluminescence research has opened entirely new avenues of investigation. Scientists can now trace the evolutionary history of light-producing genes, understanding how different species acquired and modified their bioluminescent abilities over millions of years. This genetic archaeology reveals that bioluminescence evolved independently dozens of times, with each lineage developing its own unique solutions to the challenge of biological light production. Some of the most exciting recent discoveries have come from expeditions to extreme environments previously thought too harsh to support complex bioluminescent displays. Researchers exploring deep-sea volcanic vents have found bacteria that produce light in conditions of extreme heat and pressure that would destroy most biological systems. These discoveries expand our understanding of life's limits and suggest that bioluminescence might exist in environments far more extreme than previously imagined. Cave exploration has revealed underground ecosystems where bioluminescence serves functions impossible in surface environments. In New Zealand's Waitomo caves, larvae of fungus gnats create stellar displays on cave ceilings, their silk threads adorned with droplets of bioluminescent glue. These living constellations attract prey insects that mistake the glows for exits to the surface, flying directly into the predator's traps. The precision required to study such delicate displays has pushed technology to its limits. Researchers use fiber optic light guides thinner than human hair to deliver specific wavelengths of light without disturbing cave ecosystems. Cameras cooled to temperatures approaching absolute zero can detect individual photons, recording displays so dim they would be invisible to any other detection method. Modern bioluminescence research increasingly relies on collaborations between biologists, chemists, engineers, and computer scientists. The complexity of natural light-producing systems requires expertise from multiple disciplines to fully understand. Chemists analyze the molecular reactions that create light. Engineers design instruments capable of detecting and measuring bioluminescent displays. Computer scientists develop algorithms that can identify patterns in vast datasets of bioluminescent observations. These interdisciplinary approaches have led to breakthroughs that would have been impossible using traditional single-discipline methods. The discovery of new types of luciferin molecules, the identification of previously unknown bioluminescent species, and the development of applications ranging from medical diagnostics to environmental monitoring, all result from collaborative research that crosses traditional academic boundaries. Field stations dedicated to bioluminescence research now operate in locations around the globe, from tropical marine laboratories to Arctic research facilities. These installations provide researchers with access to local bioluminescent species while offering controlled conditions for detailed studies. Many stations operate citizen science programs that engage local communities in research activities, training volunteers to collect data and observe phenomena that would otherwise require professional scientists. The global network of bioluminescence researchers shares data and techniques through digital platforms that enable real-time collaboration across continents. Discoveries made in one location can be immediately tested and verified by researchers thousands of miles away. This collaborative approach has accelerated the pace of discovery while ensuring that findings are rigorously validated before being accepted into the scientific literature. Perhaps most importantly, modern bioluminescence research has revealed the interconnectedness of these phenomena across all of Earth's ecosystems. The chemistry discovered in fireflies informs our understanding of deep-sea creatures. Techniques developed for studying marine bioluminescence apply to forest fungi and cave-dwelling insects. Each new discovery adds pieces to a global puzzle that reveals bioluminescence as one of life's most fundamental and widespread innovations. As we prepare to explore how scientists are learning to harness these natural systems for human benefit, remember that every breakthrough we'll discover builds upon the patient fieldwork of researchers who spend their lives chasing light through forests and oceans. Their dedication to understanding nature's most beautiful phenomena continues to reveal new wonders while pointing toward applications that could transform human technology. Tomorrow, we'll journey into laboratories where the light-hunting discoveries of field researchers are being transformed into innovations that promise to illuminate our future in ways both practical and profound. In a sterile laboratory in Boston, something that would have seemed like magic to our ancestors is growing under carefully controlled conditions. Tobacco plants stretch toward fluorescent lights, their leaves a familiar green during daylight hours. But when darkness falls and the laboratory lights dim, these plants begin to glow with an ethereal light that seems to emanate from within their very cells. Scientists have achieved what alchemists only dreamed of. They have stolen fire from nature itself, inserting the genes of fireflies into the DNA of plants. The result challenges our fundamental assumptions about the boundaries between different forms of life. These glowing trees represent humanity's first steps toward harnessing the 3-billion-year-old technology of bioluminescence for our own purposes. The path to creating luminous plants began with painstaking research into the genetic code of fireflies. Scientists identified the specific genes responsible for producing luciferase and luciferin, the molecular machinery that creates cold light in living systems. Using techniques that would have been pure science fiction just decades ago, they extracted these genes and inserted them into plant cells, creating hybrid organisms that combine photosynthesis with bioluminescence. The tobacco plants in that Boston laboratory can emit soft green light for over 12 hours, powered entirely by their own metabolic processes. During daylight, they photosynthesize normally, converting sunlight into chemical energy. As darkness falls, they switch to bioluminescent mode, using stored energy to power the same light-producing reactions that illuminate fireflies on summer evenings. Imagine the implications of this technology as it develops. Streets could be lit by glowing trees that photosynthesize during the day and illuminate pathways through the night. Parks and gardens could provide their own lighting without electrical infrastructure. Emergency lighting systems could operate indefinitely without external power sources, growing brighter as they mature rather than dimming with age. But the applications of stolen bioluminescence extend far beyond botanical lighting systems. In medical research facilities around the world, scientists have transformed the green fluorescent protein discovered by Osamu Shimomura into one of the most powerful tools in modern medicine. Cancer cells tagged with firefly proteins light up on imaging screens like beacons in the darkness, allowing doctors to track tumors as they grow, shrink, or spread through the body. The precision of this technique borders on the miraculous. Researchers can detect fewer than 1,000 cancer cells hiding anywhere in the human body, a sensitivity that represents detection of individual drops in an ocean of healthy tissue. Drug companies use the same glowing proteins to test new medicines, watching in real time as experimental treatments reach their targets and begin their therapeutic work. Consider what this means for patients facing cancer treatment. Instead of waiting weeks or months to determine whether a therapy is effective, doctors can observe its progress within days or even hours. Treatments that aren't working can be abandoned quickly, saving patients from unnecessary side effects. Promising therapies can be identified and optimized based on direct observation of their cellular targets. The development of bioluminescent medical diagnostics represents a perfect example of how understanding natural phenomena can lead to transformative human applications. The same chemistry that allows deep-sea creatures to communicate in the darkness now enables physicians to peer inside living bodies with unprecedented clarity. Evolution's solution to the challenge of biological signaling has become medicine's window into the molecular processes of disease and healing. Environmental scientists have discovered equally innovative applications for nature's light-producing systems. In water treatment facilities and environmental monitoring stations, engineered bacteria serve as living pollution detectors, their light output responding instantly to the presence of toxic chemicals. These biological sensors can detect contamination levels that would be invisible to electronic instruments, providing early warning systems for threats to public health. The elegance of these bacterial detection systems lies in their simplicity and sensitivity. A single drop of polluted water can silence millions of bacterial lights within minutes, providing faster and more accurate detection than any artificial sensor. The bacteria require no external power source, no complex calibration, procedures, and no expensive maintenance. They simply grow, glow, and respond to their environment with the reliability that billions of years of evolution have built into their cellular machinery. Agricultural applications of bioluminescent technology promise to revolutionize how we monitor and manage food production. Crops engineered with light-producing genes can signal their nutritional status, stress levels, and disease resistance through patterns of luminescence visible to satellite sensors. Farmers could monitor the health of entire fields from space, identifying problems before they become visible to the naked eye, and responding with precision treatments that minimize environmental impact. The development of these applications requires overcoming challenges that push the boundaries of multiple scientific disciplines. Genetic engineers must learn to insert foreign DNA into target organisms without disrupting their normal functions. Biochemists work to optimize light-producing reactions for specific applications and environments. Computer scientists develop algorithms that can interpret bioluminescent signals and translate them into actionable information. Perhaps most remarkably, researchers have begun developing bioluminescent systems that could operate in the vacuum of space. Space agencies investigate the possibility of using engineered organisms to provide lighting for long-duration missions, where traditional power sources would be impractical or impossible to maintain. These biological systems could potentially operate for years without external input, drawing energy from organic waste and providing reliable illumination for astronauts exploring distant worlds. The challenge of creating space-compatible bioluminescence has led to innovations in synthetic biology that blur the boundaries between living and artificial systems. Scientists engineer hybrid organisms that combine the efficiency of biological light production with the durability needed to survive in extreme environments. These creations represent a new category of technology, neither purely biological nor purely artificial, but something entirely new. Advances in biotechnology have also enabled the development of bioluminescent art installations that challenge our perceptions of the relationship between science and creativity. Artists collaborate with scientists to create living sculptures that pulse and glow with patterns controlled by environmental conditions or human interaction. These installations demonstrate that the applications of bioluminescence extend beyond purely practical concerns into realms of beauty and expression. Museums around the world now feature exhibits where visitors can interact with bioluminescent organisms and observe light-producing reactions in real time. These displays serve both educational and inspirational purposes, helping people understand the science behind natural phenomena while fostering appreciation for the beauty inherent in biological systems. The commercial development of bioluminescent technologies has created entirely new industries focused on sustainable lighting and biological sensing. Companies compete to develop more efficient light-producing organisms, longer-lasting bioluminescent displays, and applications for markets ranging from emergency response to architectural lighting. The economic potential of these technologies continues to attract investment and drive innovation, but perhaps the most profound impact of learning to harness bioluminescence lies in what it reveals about the relationship between human technology and natural systems. For centuries, human innovation has focused on conquering or replacing natural processes with artificial alternatives. The development of bioluminescent applications represents a different approach, one that seeks to partner with natural systems rather than supplant them. This collaborative approach to technology development opens possibilities that purely artificial systems cannot achieve. Biological light production systems can repair themselves, adapt to changing conditions, and improve their performance over time. They operate with efficiencies that exceed our best artificial alternatives, while producing no toxic waste products or requiring rare earth elements. The study of bioluminescence has also revealed fundamental principles that apply to energy conversion and storage across many different contexts. The mechanisms that allow fireflies to produce cold light inform the development of more efficient LED systems. The chemical pathways discovered in glowing bacteria inspire new approaches to sustainable manufacturing and waste reduction. Research into bioluminescent systems continues to yield unexpected discoveries that expand our understanding of life's possibilities. Scientists recently discovered bacteria that can produce light using chemical pathways previously unknown to science, opening new avenues for biotechnological applications. Deep-sea expeditions continue to find organisms with light-producing abilities that challenge existing theories about the limits of biological systems. The integration of artificial intelligence with bioluminescent research has created new possibilities for understanding and controlling these natural systems. Machine learning algorithms can analyze patterns in bioluminescent displays that would be invisible to human observers, identifying subtle signals that encode information about environmental conditions, organism, health, or ecological relationships. Researchers now envision bioluminescent cities where living systems provide much of the lighting infrastructure, reducing energy consumption while creating urban environments that pulse and breathe with natural rhythms. Buildings could incorporate bioluminescent elements that respond to occupancy levels, weather conditions, or time of day, creating architecture that adapts to human needs with the flexibility of living systems. The development of these futuristic applications requires solving complex challenges in synthetic biology, environmental engineering, and urban planning. Scientists must learn to create bioluminescent systems that can survive in urban environments while maintaining their light-producing capabilities over extended periods. Engineers must design infrastructure that can support biological systems while meeting the reliability requirements of modern cities. Perhaps most importantly, the successful implementation of bioluminescent technologies requires developing new frameworks for regulating and managing systems that are simultaneously biological and technological. Traditional approaches to safety testing, environmental impact assessment, and quality control must be adapted to address the unique characteristics of living technologies. As we prepare to explore the deeper significance of bioluminescence in the grand scheme of life on Earth, remember that every application we've discussed represents humanity's growing ability to read and write in the genetic language that life has been developing for billions of years. We are learning to participate in evolution's ongoing experiment with light and life, adding our own chapters to a story that began in ancient seas and continues to unfold in laboratories and research facilities around the world. Tomorrow, we'll step back from the immediate applications of bioluminescent technology to contemplate the broader implications of this ancient biological innovation, exploring what the study of living light reveals about the nature of life itself and our place in the cosmic story that connects all glowing creatures across space and time. As we reach the end of our journey through the luminous world of bioluminescence, pause for a moment to consider a profound truth. Every glowing creature we have encountered carries within its cells the same basic chemistry that first sparked in Earth's ancient oceans 3.5 billion years ago. From the tiniest bacteria to the largest deep-sea fish, from forest mushrooms to laboratory-engineered plants, all share participation in what may be life's most beautiful and enduring innovation. This universality reveals something fundamental about the nature of existence itself. In a universe governed by physical laws that seem cold and mechanistic, life consistently chooses solutions that combine efficiency with elegance, function with beauty. The fact that organisms separated by vast evolutionary distances and living in completely different environments all discovered ways to make light tells us something profound about the creative potential that underlies all biological systems. Consider the mathematics that govern every bioluminescent display. Light intensity decreases according to the inverse square law, double the distance, and brightness falls to 1/4 of its original value. Every creature that produces light must solve optimization problems that would challenge human engineers. How bright should a signal be to reach its intended target without wasting precious energy? How long should flashes last to convey information without exhausting cellular resources? Evolution has solved these mathematical challenges through millions of years of trial and refinement. A firefly that doubles its flash brightness burns 4 times more energy, but can attract mates from twice the distance. The optimal solution depends on population density, predation, pressure, habitat structure, and dozens of other variables that change constantly across landscapes and seasons. Yet somehow, through the simple mechanism of survival and reproduction, these calculations are performed automatically by creatures that know nothing of mathematics but everything of efficiency. The precision of these biological calculations becomes even more remarkable when we consider the quantum mechanical processes that underlie all bioluminescence. Every flash of light represents the coordinated behavior of electrons jumping between energy levels within luciferin molecules. These quantum transitions occur with timing measured in femtoseconds, millionths of a billionth of a second, yet they are orchestrated by cellular machinery that operates with clockwork precision across timescales of minutes, hours, and years. This coordination across vastly different scales of space and time reveals the extraordinary sophistication hidden within seemingly simple biological systems. A firefly's flash begins with molecular events occurring within cellular organelles smaller than the wavelength of visible light, yet produces signals that can be seen from distances measured in hundreds of meters. The same chemistry that operates in bacteria, invisible to the naked eye, powers displays visible from space when millions of organisms bloom together in oceanic conditions. But perhaps the most profound aspect of bioluminescence lies not in its mechanisms but in its apparent unnecessary beauty. From a purely utilitarian perspective, many bioluminescent displays seem far more elaborate than mere survival would require. Fireflies could presumably locate mates through chemical signals alone. Deep-sea creatures could navigate using pressure sensors or magnetic fields. Fungi could disperse spores through wind or water without any luminous assistance. Yet evolution consistently favors solutions that transcend mere functionality to achieve something approaching artistry. The synchronous flashing of mountain fireflies creates displays of breathtaking beauty that serve reproductive purposes but exceed any practical requirement for coordination. Deep-sea creatures produce light shows of stunning complexity that accomplish their biological functions, while creating spectacles that inspire wonder in any human fortunate enough to witness them. This suggests something profound about the relationship between beauty and truth in natural systems. The most efficient solutions often turn out to be the most elegant. The chemical pathways that produce biological light with 96% efficiency also create displays of extraordinary aesthetic appeal. The mathematical principles that govern optimal signaling strategies also generate patterns that please human sensibilities, evolved in completely different contexts. Perhaps this convergence between beauty and function reflects a deeper unity in the principles that govern both natural and aesthetic phenomena. The same mathematical relationships that create efficient bioluminescent displays also appear in art, music, and architecture across human cultures. The golden ratio that describes optimal spiral patterns in nautilus shells also pleases human visual perception. The harmonic ratios that create consonant musical intervals also appear in the frequency relationships of bioluminescent flashes. This suggests that our aesthetic sense may be tuned to recognize and appreciate the same principles of efficiency and elegance that evolution discovers through natural selection. When we find bioluminescent displays beautiful, we may be responding to mathematical relationships that our brains recognize as optimal solutions to universal problems of communication, energy use, and information transfer. The study of bioluminescence also reveals the extent to which beauty and complexity can emerge from simple rules applied across vast scales of space and time. The basic chemistry of luciferin and luciferase, discovered by Raphael Dubois in his 19th century laboratory, provides the foundation for displays of incredible diversity and sophistication. Each species has modified this fundamental reaction to suit its particular needs, creating variations on a universal theme that spans the entire spectrum of life's creativity. This patterned simple rules generating complex outcomes appears throughout natural systems and may represent a fundamental principle of how organization emerges in the universe. The same mathematical processes that govern the formation of galaxies and the structure of atoms also shape the patterns we observe in bioluminescent displays. Life participates in cosmic principles that operate at every scale from quantum to galactic. As we peer deeper into space, searching for signs of life among distant stars, bioluminescence reminds us that living worlds might announce their presence through light. If Earth's oceans shine with biological illumination visible from orbit, perhaps other planets pulse with their own living constellations. The same chemistry that creates our midnight sea's luminescence could beacon across interstellar distances, advertising the presence of life to any civilization capable of detecting such signals. The possibility of extraterrestrial bioluminescence opens fascinating questions about the universality of life's solutions to the challenge of communication in darkness. Would alien organisms discover the same chemical pathways that produce light on Earth? Would they develop similar strategies for using bioluminescence in reproduction, defense, and navigation? Or would entirely different worlds evolve completely novel approaches to biological light production? These questions remain unanswered, but the ubiquity of bioluminescence on Earth suggests that the ability to produce light provides such significant advantages that it would likely evolve on any world where complex life emerges. The fundamental physics of light transmission through matter remains constant throughout the universe, creating similar optimization problems that might lead to similar solutions regardless of the specific chemistry of alien life forms. Even if we never encounter bioluminescent life beyond Earth, the phenomenon continues to reveal new layers of complexity and beauty in our own world. Every year brings discoveries of new species with previously unknown light-producing abilities. Deep-sea expeditions find creatures that create displays of unprecedented sophistication. Laboratory research uncovers new chemical pathways that expand our understanding of what's possible in biological systems. The applications of this expanding knowledge continue to transform human technology and medicine. Bioluminescent diagnostic tools become more sensitive and specific, enabling earlier detection of diseases and more precise monitoring of treatment effectiveness. Environmental sensing systems based on living organisms provide increasingly detailed information about ecosystem health and environmental change. Sustainable lighting technologies based on biological principles point toward futures where human activities align more closely with natural processes. But beyond these practical applications, the study of bioluminescence offers something equally valuable: a sense of wonder and connection to the broader community of life on Earth. Every firefly flash connects us to the same evolutionary heritage that links all bioluminescent creatures. Every bioluminescent bay reminds us that we share our planet with beings whose abilities routinely exceed the boundaries of human imagination. This sense of connection becomes particularly important as we face global challenges that require understanding life as an interconnected system rather than a collection of separate species competing for resources. Bioluminescent organisms depend on healthy ecosystems that provide the nutrients, conditions, and evolutionary pressures that maintain their light-producing abilities. Climate change, pollution, and habitat destruction threaten these systems in ways that could dim or extinguish natural light, shows that have illuminated Earth for hundreds of millions of years. The conservation of bioluminescent species and their habitats becomes not just an environmental imperative but a preservation of wonder itself. Future generations deserve the opportunity to witness synchronous fireflies transforming mountain forests into towers, pulsing galaxies of light. They should experience the magic of swimming through bioluminescent plankton that turn breaking waves into cascades of liquid starlight. They need access to the profound sense of connection and humility that comes from encountering organisms whose abilities remind us that we are part of something much larger and more creative than human civilization alone. Perhaps this is the deepest lesson that bioluminescence offers, that we inhabit a universe where beauty and function intertwine at the most fundamental levels of existence. The same forces that shape stars and planets also guide the evolution of creatures that paint with light in Earth's darkest places. The mathematical principles that govern quantum mechanics and cosmic evolution also determine the optimal patterns for firefly courtship displays and deep-sea communication networks. In studying bioluminescence, we discover that science and wonder need not be separate pursuits. Understanding the mechanisms behind natural phenomena can deepen rather than diminish our appreciation for their beauty. Knowledge of the chemistry that powers bioluminescent displays enhances, rather than reduces, the sense of magic we experience when witnessing them in nature. As you drift toward sleep tonight, carry with you the knowledge that somewhere in the darkness around you, the descendants of those first glowing bacteria continue their ancient work. In puddles and ponds, forests and seas, they flash their quiet signals and tend their molecular fires. They remind us that light, true light, comes not from burning but from living, not from consuming resources but from organizing them into patterns that create beauty while serving life. The story of bioluminescence continues to unfold in laboratories and research stations around the world, in deep ocean trenches and mountain meadows, in the genetic code of organisms we have yet to discover, and in applications we have yet to imagine. It is a story that began before complex life existed on Earth, and will continue as long as living creatures find advantages in creating light from chemistry. We are privileged to live at a time when we can finally understand the mechanisms behind phenomena and that inspired wonder in our ancestors, while participating in the development of technologies that harness these same mechanisms for human benefit. We stand at the intersection of ancient mystery and modern knowledge, capable of both appreciating bioluminescence as poetry and applying it as engineering. In this convergence of wonder and understanding, beauty and utility, mystery and knowledge, we glimpse something essential about our relationship with the natural world. We are not separate from the evolutionary processes that created bioluminescence, we are part of them. The same creative forces that taught bacteria to glow and fireflies to flash also shape human consciousness and drive our endless curiosity about the world around us. The eternal dance of light and life continues, and we are both observers and participants, students and teachers, beneficiaries and guardians of phenomena that connect us to the deepest truths about existence in a universe that consistently chooses beauty alongside survival, elegance alongside efficiency, wonder alongside wisdom. In this understanding, perhaps we find not just scientific knowledge, but something approaching peace, the recognition that we belong to a cosmos where even the smallest creatures participate in displays of creativity that humble human art, and where the most practical solutions often turn out to be the most beautiful. The light that illuminates our world comes not just from stars, but from life itself, reminding us that we dwell within a universe where consciousness has emerged to contemplate its own luminous wonders.